Okay, we've got a situation with a diffraction grating where we're going to apply our formula. Okay, all right, the formula we're going to be using is the one that's in your data sheet, that d sine of theta equals n lambda. Okay, and we're talking about the zeros and first order maxima. By maxima it means positions of maximum intensity on the screen. And we know that there's a central dot when we shine our line through a diffraction grating. That's called the 0th order maximum, and it happens when n is naught and sine theta is naught, and so the angle, there's no deflection in the angle at all. So we don't need to do that calculation, but if we did, we'd take n to be naught, we'd discover that sine theta was naught, and that the angle theta was naught, all a bit boring. We've now got to think about the first order maximum. So that means that n is going to equal 1. Okay. And the other things we need for the formula, we need lambda. Oh, I've got that. Lambda equals 500 nanometers. So that's 500, but nano is 10 to the power minus 9, so it's 500 times 10 to the power 9 meters. Okay. Which would be 5 times 10 to the minus 7 if I want to convert it. And I need something else. I need d. Now d, remember, if you've got gaps between slits, d is the distance between two gaps in the diffraction grating, or the separation, if you like, of the lines in the diffraction grating. Now, I'm not given that directly, but I'm told there are 4,000 lines per centimetre. So my d is going to equal, well, I know that 4,000 d, 4,000 of these lines are a distance of 1 centimetre. So that would be 10 to the power minus 2 meters per centimetre. So the distance between consecutive gaps in this grating, d is going to be 10 to the power minus 2 divided by 4,000, which you can't see me doing, but there it is, did it, honestly, which gives you, do that on a calculator, but it's not, it's, well, let's do it properly in standard form. You're going to get 2.5, okay, times 10 to the power of, it's going to be minus 6. Okay, you can check that on a calculator if you want, but I promise you that's true. So now I've got three things I can put into my formula. So d, which is 2.5 times 10 to the power minus 6, times sine of theta equals n, which I don't know, n, oh yes I do, n is 1, so 1 times, and lambda is this 5 times 10 to the power minus 7 number. Or you can leave this 500 times 10 to the power minus 9 if you want. So, next thing I can get is sine of theta. Remember, what I wanted to find was the angle between the centre spot and this first order one. So I'm finding this angle theta, that's what I'm getting. So finding sine theta will be good for that. Okay, so sine theta will equal this 5 times 10 to the power minus 7 over 2.5 times 10 to the power of minus 6. Okay, oh, I'm doing quite well. I can do this in my head. This is 0.2. Okay, checking the calculator if you like. And then the only bit that I am going to need a calculator for, I think I'll find it. I'll have it over here. Okay, I'm going to need to find out from sine of theta equaling 0.2, I need to check I'm in degrees. Yes, I am. So I need to do inverse sine of 0.2. There it is. And there it tells me that I'm going to get a separation in angle terms of 11.5 degrees. Okay, so theta equals 11.5 degrees. Okay, oops, there it is. There's the answer to the first part of the question. Alright, okay. But then I need to think about this other bit, the total number of maxima. Okay, so that is to do with what I can get n up to. So I can get a first order fringe, and it turns out to be at this angle, but I can get a first order fringe because when I put n equals 1 into the formula, then I get this answer sine theta equals 0.2. Okay, and so I get a value for sine theta. But and when if I put n equals 2 into the formula, it would be a very simple calculation. So let's get rid of that. But if I put n equals 2 into the formula here, I'd get a 2 there, Okay, I'd have a 2 times on the top, and I'd get an answer of 0.4. Okay, but I couldn't just keep going because there's a limit to how big sine theta can be. Okay, in fact, when I get up to n equals 5, okay, all right, then for n equals 5, I'd get 5 times 10, 5 times here, and I get 5 times here, so the answer would be 5 times as big as it was for n equals 1, so I get an answer of 1, which is the absolute biggest sine theta can ever be. So for n equals 6, if I tried to do that, I'd get an answer of 1.2 down here, and for that I wouldn't get, I'd get an error when I tried to find theta. So that's telling us that the maximum conceivable n is 5. Now this particular case where sine theta equals 1 is absolutely the limiting case. But for that one, we really need to take seriously the idea that light is coming here at the diffraction grating and actually being deflected by the full 90 degrees. Now, if you actually try this in practice, you'll discover that doesn't happen to any detectable extent. So therefore, we're going to ignore the solution n is 5, which means that the highest order fringe is the 4th order fringe is the highest we can get. Okay? But the question wasn't what's the highest order fringe we can get. The question was what's the total number of maxima, what's the total number of spots we get. So we've got to remember to count the centre one, which is when n is 0. Okay? And then the first order fringe here, when n is 1, is all very well and good. But there'll be another first order spot down here for n equals 1. So the total number of fringes we'll get will be 1, okay, for the one fringe for n equals 0, okay, and then we'll get 2 fringes for n equals 1, and 2 for n equals 2, and 2 for n equals 3, and 2 for n equals 4, so that'll be plus 2, plus 2, plus 2, plus 2, but after n equals 4, okay, we've argued that n equals 5, and certainly higher than that, we won't see the fringes, so the total number of maxima we'll see will be 9. And that completes that question.